Hi, I'm Gaston Fermandois from Santa Maria University in Santiago de Chile. The title of this talk is Adaptive Compensation with Magnetorheological Dampers in Real-Time Hybrid Simulation Testing. Let's begin. Real-time hybrid simulation is a realistic and cost-effective dynamic testing. It consists in partitioning the reference structure into numerical and experimental substructure, where the experimental components of interest are loaded and tested in the laboratory. Meanwhile, the rest of the structure is modeled numerically in a computer. Is of special relevance to the study of structures that is equipped with magnetorheological dampers, which is a type of semi-active device that is used in structures to mitigate vibrations. The critical component in this case will be the MR damper, which in this case is highly nonlinear and rate dependent. And the challenge of real-time hybrid simulation in this case is to synchronize both numerical and experimental substructure. The synchronization problem is solved using a dynamic compensator, but usually these dynamic compensators are designed for linear experimental substructures. So the question that arises is how to design a dynamic compensator that is sufficiently robust to incorporate all the nonlinearity and rate dependency of the specimen. So the study objectives are the following. Prove the efficacy of an adaptive model-based compensation with robust calibration in a virtual real-time hybrid simulation test of a linear building equipped with an MR damper, and to implement a semi-active control law to assess the performance of the virtual RTHS with MR dampers. The model for the virtual RTHS is the following. We have a numerical substructure with an input considered to be a ground excitation. The numerical substructure is equipped with an MR damper. The response of the structure is defined as xt, which is the target displacement. This goes through an adaptive compensator, which creates a signal xc, which is the control signal, to the actuator, and the actuator will create a force to the MR damper. The measured displacement of the actuator is xm, which is fed back to the adaptive compensator, and this is something that we call the compensation loop. As I mentioned before, the displacement of the actuator will drive the MR damper, and we will consider from the sensors that are installed in the numerical substructure, which are signals Y, a semi-active control law that will create a voltage over the MR damper, which will create finally the semi-active force that goes to the numerical substructure. This is something that we call the semi-active loop. In this case, for the virtual RTHS, the control plant consists both on the actuator, the MR damper model, and the semi-active law that drives the MR damper. For this particular case, we consider the El Centro earthquake 1940 scaled to 40% of the PGA. And the actuator is modeled using a servo-hydraulic actuator model, physical model, derived from Carrion and Spencer in 2007. And the adaptive compensation is designed as an adaptive model-based compensator, which is proposed in a companion paper. So, regarding the performance, this figure shows the target versus measured displacement comparison, where we can see that there is a very good tracking between measure and target displacements, which give us some clues that the adaptive compensator is doing its job, where the error at some point is less than 0.4 millimeters. The evolution of the adaptive gains is shown in the following figures, where we can see fast adaptation of the parameters, and we can also see that the parameters converge to a certain value that is the dynamics of the actuator, including the specimen interaction. In this figure, we can see the performance of the proposed compensation, where on the left we can see the normalized root mean square error between the target displacement and the measured displacement in RTHS, while on the right we can see the normalized root mean square error between the reference structure and the measured displacement from RTHS. There are two scenarios, which is non-compensated, which is the dark colors, and the proposed compensation with the semi-active control law. And we consider also three scenarios of control law for the MR damper: passive off, which is basically zero voltage to the MR damper; passive on, adding the maximum voltage to the MR damper; and the COC, which is the clip optimal semi-active control law. So the results show excellent synchronization for the J2 indicator, with a reduction on the tracking error of at least 34%. And also we see high fidelity from the reference structure and the virtual RTHS, where we have a decrease of 22% on the J4 indicator when we include compensation. So in conclusion, the implementation of a robust adaptive model-based compensation for RTHS using highly nonlinear specimen is presented. The compensation method involves no prior knowledge of the test specimen. We conducted virtual RTHS using a framework with Matlab and Simulink. The tracking delay reduction demonstrates that a adaptive model-based compensation offers necessary robustness guarantees for virtual RTHS with highly nonlinear and time-varying specimens such as MR dampers. And for future work, we are going to conduct experimental validation in the laboratory using this framework and a small-scale MR damper that will be installed in the laboratory. And with that, I would like to thank you for your attention. For further information, you can check the companion paper to this presentation, and if you have any other questions, you can reach me through email or Twitter. Thanks.